Hi, everybody. Today we are talking about section 15.4 in the dynamics book, and the topic of this is acceleration of generalized plane motion. So this lecture will be at position number 22 on our Moodle page, and we will cover slides 29 through approximately 43 of the PowerPoint lectures. Now, we won't talk about all of the PowerPoints. After 29, we'll have a little bit of information, and then there are several worked problems. So I would recommend that you go through the worked problems in order to take a look at some different examples, so that when you're doing your homework problems, you can use those to help you get started. So in the past sections, we were talking about velocity, and we often split velocity into two components. We split it into a translational component and then a rotation about that same point. So if point A, for example, translates, we can say that the velocity, we could have said the velocity of B is equal to the velocity of A in pure translation plus the rotation of B about point A. Then we took one lecture and talked about an instantaneous center of rotation, where we viewed the velocity of B and the velocity of A as both being pure rotation about some other point. Well, as I said, it's not quite a parlor trick, but it is definitely a way to simplify the math, but it only applies to velocity. It doesn't apply to acceleration at all. So if we're going to talk about acceleration, we have to go to the pure math form of our equations. And we can recognize that in a plane, if the plane in which the object moves is the xy plane, that all of the rotation is going to be in the z direction. So in other words, the rotational component of the acceleration is going to be perpendicular to the plane of motion of the particle or the slab or the rigid body itself. So the first thing that we do is we develop a technique where we find it's sort of the same idea where previously we had the velocity of A, and we said the velocity of B then is equal to the velocity of A plus the velocity of B with respect to A. We can say the same thing about acceleration. That in this case, if we have plane, well, you can do it in generalized 3D motion as well, but we're limiting our talk to plane motion, that the acceleration of point B can be thought of as the acceleration of point A plus the acceleration of B with respect to A. So we can translate this into an acceleration of point A, which is purely in translation, and then a rotation about A of point B. So how we break that up is we can say that we break this up into a normal and a tangential component. So the acceleration of B with respect to A in the tangential component is alpha, which is the angular acceleration measured in radians per second squared, crossed with the vector that goes from B to A. So from B to A is r of B with respect to A. And that the normal acceleration is minus omega squared r, where r is the same, the vector B with B to A. So since this direction is well defined, we can then say that the tangential, because we're in a plane, if you're in non-planar motion, if you're in three-dimensional motion, this becomes quite a bit more complicated mathematically. But the value, not the vector, you notice there's a little vector symbol here, no vector symbol over here on the right, but the acceleration of B with respect to A in the tangential direction is r, the value of r times the value of alpha, and the normal acceleration is r times omega squared. And you can see that the units work out. This is per second squared, this is some length, so this is a length per second squared, which is a good unit for an acceleration. And here we have per second, which is per second squared, times r, which is distance. So once again, we have a distance per time squared. So the dimensions all work out. And So we can use this in different ways, like on this sliding bar. We can find accelerations. If we want to find the acceleration of b, we can say, well, it's equals the acceleration of a, which is linear, so we can define that pretty well, plus that acceleration of b with respect to a. So we can think about putting the acceleration of a vector attached to b, just translate it to point b, and then take the rest of it as this acceleration, recognizing that the acceleration has two components, one in the tangential direction or along the path of motion, and one in the normal direction perpendicular to the path of motion. And they show you a little bit of a geometric solution here, but you probably know by now that I like to keep things a little bit more vectorized. So if we look at x components, we look at this and we say, oh, the acceleration of a is all x, right? It doesn't occur in the y direction at all. The acceleration of b is all b. So that's the first thing that we can do. And then we can say L times the sine of theta, or L times the cosine of theta, are actually the components of a with respect to b. So L times the sine of theta is this dimension right here, and L times the cosine of theta is this dimension right here. So L omega squared cosine theta is really just saying r omega squared, and this is r alpha, r omega squared, and r alpha. And then we can use that to solve for the acceleration of b, which is our unknown. We know it's purely y, but we don't know its value, and we can solve for alpha. So this is just going through the math and coming up with those equations. Now this is actually an excellent slide, so when you're using your homework, take a look at this and use it as an example. It's an excellent example of kinematics. All right, here's that gear problem that we keep coming up against, where we have a double gear, inner gear, outer gear, that spin at the same angular velocity, and we have a velocity, which is a translational velocity, and a translational acceleration. We want the angular acceleration, which is alpha, and the acceleration total of points B, C, and D. So once again, we're going to use this idea that the acceleration of B, C, and D is going to be the acceleration of A plus the acceleration of B with respect to A, the acceleration of C with respect to A, and the acceleration of D with respect to A. So we break this up. We know just from our previous discussion that r theta is equal to x sub a. Take the first derivative of x is velocity of point A because it's purely in the x direction, and we can come up with an expression for omega. After we do that, we know that the acceleration of A is equal to r1 times omega, the second derivative of omega, which is alpha. We can solve for alpha. So it's spinning at 20 radians per second in the negative sense. Why is it negative? Because the spin is clockwise. So that goes along with our vectors. Now, here's some more information. I want to show you a problem that's treated in a highly vectorized way by the chapter. So let's take a look here at problem 15.8. We have a crank, we have some dimensions. We know that the velocity of point D is going to equal the velocity of point B plus the velocity of D with respect to B, and similarly for the acceleration. But our directions are a little bit more complicated here, so we're going to break those up into I and J components. So for example, we have omega D, but then we have the moment arm, which is the r of D, so it's going to be whatever we're taking that about, D with respect to E. Okay, so we're going to say, how does this move with respect to this? And that's going to be this vector. So we have 17 and 17. From D to E, or from E to D. Okay, so from E to D, we have negative 17I and positive 17J. All right, so then we do our cross and we get a velocity. Now we also, that's going to be the velocity of point B, isn't it? Okay, so what we're doing is we're trying to tease out some different things here. Then we have the velocity of D with respect to B, And in this case, we have B, and we're going to say what's D doing with respect to B. So we're going positive in the I direction, 12 units, and up or positive in the J direction, 3 units. So we come up with our R value. We have omega right here, and then we can break it down into components and solve. So if you look at those two problems, you have one that's handled sort of with minimal vector math, and then this which is handled almost entirely with vector math. So those two are good examples. Then we take a look at the acceleration. It's the same idea. We have a little bit different equation, but it's still that highly vectorized R values. Omega is coming straight out of the board because we're in the plane. So omega is either positive z or negative z. And so we do the vectors, we come up with the components, and here we can solve for alpha of BD and alpha of DE based on those components. All right, so that is it for section 15.4. The problems in this section tend to be quite lengthy, but it's really important that you draw a free body diagram because that's really where your analysis is going to start. So draw a free body diagram, get your vectors, unless it's something extraordinarily obvious, like the first problem that we worked, where we have a wheel and a double gear and these racks, and you can see the directions pretty quickly. I would suggest you go very, very quickly to vectors. And it's very easy. I don't think there's any real simplification here by doing it this way. In other words, if you know the velocity and the acceleration of A, you can see that R here is going to be just in the positive J direction. R here is going to be in the negative I direction, and R here is going to be in the negative J direction. So you can work everything out using vectors just as easily with this type of a problem as well. All right, so I'll put up a couple more homework assignments, and then on Wednesday we will finish up chapter 15. Thanks.